Today's lab is on seismology, which is the study of earthquakes. Most earthquakes on the Earth occur when motion occurs along a fault inside the Earth. The point where the actual motion is centered is called the focus of the earthquake. It is within the Earth at some depth. And the area directly above the focus on the surface of the Earth is called the epicenter. And that's what you're going to be finding today. So when an earthquake occurs, energy is transmitted through the Earth in all directions in the form of waves. Those waves can be recorded by machines called seismographs. It takes 3 seismographs to triangulate the location of an epicenter. And so once the earthquakes are recorded, there are different types of waves that are recorded, and scientists will use the time difference in the arrival time of those different waves to figure out how far away from them the earthquake actually occurred. So this is an idealized seismograph that is produced by a seismograph machine, produces a seismogram. So when an earthquake occurs, the first wave to be recorded in a seismograph is called the P wave. It's called the primary wave because it's the fastest one. It's also the smallest one. And then sometime after the first P wave is recorded, you'll notice that the waves get substantially larger in size, and those are called S waves. They stand for secondary waves. Those are recorded afterwards. So if a location is close enough to the epicenter where there's ground shaking, surface waves, which are often called L waves, will then be recorded. You'll learn more about these in our chapter on earthquakes. What you also see is that there are these very faint lines, vertical lines here, that delineate time of about a minute time difference between these tan lines. So what scientists do is they look at the arrival time of the first P wave and see how much later the first S wave arrives. So what you can see is that here is half a minute of time. This is 1.5 minutes, 2.5 minutes, 3.5 minutes, 4.5 minutes, and then 5 minutes. So it's been 5 minutes since the time that the first P wave first arrives is when the first S wave arrives. Scientists will take this 5-minute time difference and look at what's called a time travel graph. So this allows geologists and seismologists to estimate how far away from them the earthquake actually occurred. So here is a time travel graph. What you see is on the x-axis is the distance away from the epicenter, and it's in kilometers. The same x-axis, but on the top, is the distance to the epicenter, but it's in miles. Almost every country in the world uses kilometers and not miles, but this is the United States, and we're going through some stuff right now, so we use miles still. This blue line is already on the graph. This is the time difference that allows us to estimate how far away the location might be from the earthquake. So we determined up here, right, that it was 5 minutes between the arrival time for the first P wave and the first S wave. So we take that over to the y-axis here, which is the time interval in minutes between the P and S wave arrival times. And we go up to 5 minutes. And then once we hit 5 minutes, we read over until we intersect with the blue line. And then we, at this point, can either read up. If we read up, that tells us that we were maybe about 2,100 miles away from that earthquake. And if we read down, that tells us that we were about 3,400 kilometers away from that earthquake. So then what you can do with this information is draw a circle around your location with a radius of the distance that you just determined on that time travel graph. So in this example, there is an earthquake, and it is recorded in 3 different locations. It's recorded in Bismarck, North Dakota, Sacramento, California, and El Paso, Texas. So the seismologists in El Paso, Texas use their time travel graph, and they figure out that somewhere 880 miles away from them there has been an earthquake. So they draw a circle around El Paso, Texas that has a radius of 880 miles. Then the folks in Sacramento, California also record the same earthquake, but they determine it's only 250 miles away from them. What you can see is the reason we need 3 seismographs to determine the epicenter of the earthquake, because you can see that the epicenter is either here or it's here, because these circles intersect in two locations. So we need the information from Bismarck, North Dakota. And Bismarck, North Dakota determined that somewhere 1,051 miles away from them, there was an earthquake. And then what you see is the triangulation process. All three of these circles intersect here, and that is the epicenter of the earthquake. We can then record the latitude and longitude of that epicenter. And that is what your lab is going to do today. So I'm going to give you some fictional earthquake data, and then I'm going to walk you through how you do this in Google Earth. So there's an earthquake, and using time travel graphs, seismologists in Rochester, New York, determined that the earthquake was 1,146 miles away from Rochester. In Santa Fe, New Mexico, they determined it was 1,000 miles away from Santa Fe, New Mexico. And in Colombia, seismologists determined that the earthquake was 2,024 miles away from Bogota. So we're going to take that information, and then we're going to open Google Earth. So it's important to see here that all of my places are not selected. They're all empty here. I have all of these things off so that it won't sort of mix up my screen and give me more information than I need. I do, however, have my borders and labels turned on, and so are my places, because that's going to give me the names for cities when I do find that epicenter. So the data that we were given, I have written down here. So I'm going to go to Rochester, New York, up in my search bar, and I click go. And Google Earth will put a place marker right in Rochester. Well, I know that I have to be, according to my data, 1,146 miles away from Rochester. So I need to make a big circle around Rochester. So what I'm going to do is just back out a ways. I'm going to back out a ways where I can see most of the United States. Then I'm going to go up to my ruler here. In your ruler, so far we've used the line and the path option. Today, we're going to use the circle option. I want my answer to be in miles, and I also want to make sure I do not have mouse navigation selected. So then I'm going to take my cursor and go so that Rochester is in the middle. I'm going to click, and then I'm going to drag until I have a circle that is about 1,146 miles in diameter. And you can see, and it's tricky. It's very, oh my God, I got it. Perfect. And then I let go of my mouse button. And I've made a circle around Rochester that is 1,146 miles in diameter. I want to save that circle. And when I do that, this box will pop up. I'm just going to call this Rochester, New York, and click OK. And now that circle exists in Google Earth. So now I want to make a second circle, and the data that I was provided with said that we need to make a circle around Santa Fe, New Mexico. So I'm going to let Google Earth take me to Santa Fe. And again, I want to back off. All I'm doing is I'm using my mouse button here and I'm scrolling backwards so I can see most of the United States. I'm going to go back to my ruler. I have circle, I have miles. I'm going to go so that Santa Fe is in the middle of my cursor. I'm going to click and drag until I have a circle that is 1,000 miles. Oh my God, I got it again, in diameter. And I'm going to save that as Santa Fe. And if you look over here, there have been two circles created in your temporary places. So now I can see that my earthquake epicenter is either here or it's here. So I'm going to make one more circle. And, oops, sorry, let me close that. First, I want to search for Bogota, Colombia. Search for that. There I am. And now I'm going to repeat the process where I back up. I'm going to get it a little bit closer so that I can at least see these circles. And then I'm going to go back to my ruler. Everything's all set. And according to my data, I need to make a circle that is 2,024 miles in diameter. And that is right about so close. Close enough. Right around there. So I'm going to save that as Bogota. Now I can see where my epicenter is. What I'm going to do is zoom in. And oh my gosh. So you'll see a couple things. One is that I wasn't perfect, right? My Bogota was not direct dead on, but that is pretty darn close. So your epicenter is somewhere in here. What you'll be asked to record in your lab is for the city or the geologic structure where the earthquake epicenter is located. So here you would write New Orleans. And so it'll be someplace that is fairly well known and fairly obvious and well labeled on Google Earth. So the next thing you're going to be asked is for the latitude and longitude. So I have a couple choices here, right? They didn't quite overlap. But as long as you are in the right ballpark, that's fine. So what you see is down in the bottom corner, your latitude and longitude are actually recorded. So if I were going to record the latitude and longitude of this location, I would write down 29 degrees, 57 minutes, 31.54 seconds north, and 90 degrees, 3 minutes, 28.93 seconds west. And actually what's kind of cool, as you can see here, is that New Orleans is 20 feet below sea level at this location. So I can already hear you guys saying, well, what if I record the latitude and longitude of this location? Or the latitude and longitude of this location? That will be fine. Everything will be fine as long as you're in the right ballpark, which if your circles are this close, you will be. So that's your lab for today. It's pretty fun. Let me know if you have questions. Thanks.